Hello and welcome to my contribution to the Bernstein conference in 2021 with the title Inhibitory Plasticity, one mechanism to shape representational and metabolic efficiency. To begin, I would like to briefly describe the topic of my presentation. It is well known that the input stimuli in the primary visual cortex are encoded very efficiently, especially in terms of representational efficiency. What meant here the numbers of different features in the input which can be encoded by the network, and in terms of metabolic efficiency, what is meant here with the amount of information that is transmitted by one single spike. Previous researchers have already pointed out that the receptive field diversity is important for the representational efficiency, and that the metabolic efficiency is mainly influenced by a gain control mechanism through feedback inhibition. The role of excitatory plasticity has also been extensively studied in the past, whereby the influence of inhibitory plasticity is still unclear. To investigate this influence, we built a spiking neural network consisting of a population of Poisson neurons to model the LGN layer, a population of excitatory and a population of inhibitory neurons. As you can see here, excitatory and inhibitory neurons receive excitatory input from the LGN population. Additionally, there is an excitatory connection from the excitatory to the inhibitory population, an inhibitory feedback connection, as well as a lateral inhibitory connection. All the excitatory connections develop via a voltage-based triplet SCTP rule, and all inhibitory connections develop via an inhibitory SCTP rule. To enable the emergence of GABA-like receptive fields, we presented patches of natural scenes images to the network. Here on the right, you can see how a parameter change of the inhibitory rule can change the E to I ratio in the resulting neural network, one with a 2:1 ratio and one with a 3:1 ratio. In complete, there are 6 different model configurations. The first 2 that we already know, and then the third one, which based on the I to E 2:1 model, but with blocked inhibitory connections after the training, to see what is the influence of the resulting receptive fields without inhibition in the network. Furthermore, we used pre-trained weight matrices of the E to I 2:1 model, shuffled the matrices, and fixed either the connections at the feed-forward inhibitory synapses, which is indicated here black, or the synapses of the feedback inhibition, and learned in this case the model again. And finally, one model which has no inhibition at all. After stable receptive fields are emerged, we measured the preferred orientation of each excitatory neuron with sinusoidal gratings. Based on that, we calculated an orientation diversity index, where a value closer to 1 means more different orientations and a value closer to 0 less different orientations. As you can see, the models with inhibitory plasticity on all synapses showing a high orientation diversity. Despite that, if the feed-forward inhibition is fixed during the development phase, the ODE decreases. It decreases even further if the feedback inhibitory is fixed. The lowest value for the ODE shows the model with no inhibition at all, meaning that most of the neurons develop similar orientations. To measure the representational efficiency, we calculated the image reconstruction error as described here. As presented on the right, a higher dose ODE results in a lower error, or to say differently, in a better representation of the input. To measure the metabolic efficiency, we calculated the mutual information in bits per spike for 10,000 randomly chosen natural scenes. However, we see that the emergent E to I ratio leads to good result and to a high metabolic efficiency. Furthermore, by presenting sinusoidal gratings on different contrast levels, we observed the emergence of contrast invariance tuning curves for the EI 2:1 model. Here on the left, you can see the orientation bandwidth for different contrast levels. In the middle and in the right, you can see the incoming excitatory and inhibitory currents for the EI 2:1 model for different orientations and contrast ranges. As you can see, for the non-private orientations, the excitatory currents are higher for lower contrast levels. But for higher contrast levels, the inhibitory currents increases stronger and compensate the excitatory currents completely for the non-private orientations, and leading so to the observed contrast invariance behavior. In conclusion, we have shown that the plasticity on the inhibitory feed-forward and feedback connection is essential for the development of a good input representation, and that the resulting E to I ratio improves metabolic efficiency and leads to contrast invariant tuning curves as an immanent feature of the network. Finally, I would like to point out that we currently submitted a manuscript about this topic to PLOS Computational Biology, and that the preprint of this manuscript is available at bioRxiv. Thank you for your attention.